Hello everybody, welcome to the presentation. This presentation is on my paper which has been submitted and accepted in this conference. The topic of this paper is Edge Computation for SDR/SDN. SDR stands for Software Defined Radio, SDN stands for Software Defined Network. This presentation was performed this work was performed by myself, Sumit Chakravarti, and my co-author and colleague Madhushri Banerjee. My affiliation is with the Department of Electrical and Computer Engineering at Southern Polytechnics College of Engineering and Engineering Technology in Kennesaw State University, located in Georgia, United States of America. This work, my colleague's affiliation is with Gwinnett College of Georgia Gwinnett College, Department of Information Technology, School of Science and Technology in Lawrenceville, Georgia, USA. So I welcome you. So in this work, let's summarize what this work is about. In this work, we aim to use software-defined radio, software-defined network framework for performing joint computation to guide the network. We use a simulation platform like NS3 together with RYU and Mininet, a kind of simulation platform to simulate our work. We have used deep reinforcement learning using OpenAI Gym, as well as other relevant technologies to compare our results with for the reinforcement learning application with our RYU controller platform. So we will first start with the introduction. I will talk about what is this concept of software-defined radio, software-defined network. Software-defined radio, software-defined network, SDN, SDR-SDN, is becoming very popular these days. This is primarily because software-defined radio network sit actually at the cutting edge of the networking domain, where they also sit at the edge of network, wherein they control both the physical layer communication of the network as defined in software-defined radio, as well as the structural and the networking aspect of the network as defined by software-defined network, SDN. So the premise of this is that if we have a SDR-SDN platform or a controller sitting at the edge of the network, then they can control both the parameters associated with the physical layer of the network as well as the networking aspect of the network. So that is the premise, and that is what we are showing over here in this application. Now in this case, we have used OpenFlow standard which incorporates this SDR-SDN framework, and we have our RYU controller, which is one of the most popular controllers used in this domain for doing this job. Our aim is also to showcase use of reinforcement learning as a comparative measure for performing for checking the performance of this SDR-SDN framework work related to RYU. So coming to the core aspects of SDR-SDN network, as we have discussed in this paper, we kind of talk about how is the SDR-SDN network different from a classical communication network architecture. So in classical communication network architecture, you can see, as we have mentioned over here, we have three different planes. We have, of course, a control plane. In the control plane, the control signals related to the network flows through, and which kind of controls what the network control needs to perform. We have the data plane, which is actually the plane where the data packet actually flows in to and from the device. And then of course we have management plane, which takes care of wider management communication and issues. This includes looking at sending updates, looking at different aspects of the network, and all, looking at and checking different configurations of the network. Now, in this case, you have three separate layers and have these three separate technologies which kind of do the job. This, of course, creates bottleneck because you have individual brains at individual controllers, which may not be always synced. Unlike this, our SDN SDR edge network unifies these three separate layers, and this is shown in figure 2. As you can see, in SDN is concerned with transport and networking. SDR, on the other hand, is concerned with data and physical layer. But SDN SDR virtualization kind of unifies all of that, and it can address or control all these physical as well as network parameters together, including network transportation, data link, as well as physical. So coming back to our figure 1, in which we kind of show the typical usage platform. In this typical usage platform, you can see that we have the core network, which is where SDR-SDN controller, in our case the RYU controller, is sitting. Now in this case, they control both the networking parameters like the data rates going in the network and all that, the packet rates and all that, as well as they control the physical parameters associated with the SDR. So in our case, we use the open flow architecture for the SDR-SDN, which is by far the most commonly used open source architecture for this kind of simulation. Now, in this case, the open flow architecture is a standard protocol which has been used for smooth interoperability between switches, and in this case, these switches are known as open virtual switches, open V switches, and they kind of are basically, in this case, if you look at figure 3, which identifies the structure, you can see that the virtual switches are thereby controlled by a unified controller, and they kind of are able to analyze their backlog, their flow rates, and other network parameters associated with them, and go for a unified controller. For our case, we use the Mininet framework together with GIM environment as provided by the OpenAI GIM to kind of do our RL setting, and we of course have the OpenFlow protocol supported RYU controller to do the standard control for our SDN SDR network. So next we kind of talk about the simulation parameters that we associate for our network. In this case, we talk about simulation parameters, for example, channel width, guard, this is the type over here, it should be guard interval, MSC coding rates, and these are the primary key testing parameters associated with such testing. And of course, we discuss about the value and ranges that we have used for these key parameters for our testing. The protocol we test includes TCP or UDP, and we decide on a transmission power of 40 milliwatt, right, which is correspond to 60 dBm. Once we have these parameters, we can set up these different aspects of testing, including short guard, long guard, and at different frequencies of transmission, as is shown over here. And you can see, depending upon the MCS, how much is the throughput for such situations. Next, we of course show over here how the signal strength and SNR change with the distance metric, which is the primary simulation parameter for the SDR aspect of it. So the previous ones were SDN parameter that we had simulated. This one is the SDR parameter that we simulate. Once we have those simulations set up ready, we invoke the RYU software for load balancing, which is the primarily brain for our system, using the classical ways of control, but of course in this case they are not located at individual routers, individual switches. They are unified control of all the switches using the architecture as you can see in this figure 3. So that is the RYU controller's location and the RYU controller performance control from there. So in this case, this figure 6 shows the load balancing script for the RYU controller, and you can see from here they kind of set up the controller, set up the packet rate, set up the quality of the packet, set up the IP and other kind of structure that is used, and then once the setup is complete, they kind of run it for the different setup parameters that we discussed, and then we perform the simulation. For our simulation, we take this network topology. So in our network topology, we have four edge nodes which are connected through these two routers, and they have different paths between them. Now in this case, different paths have the different costs. So we want to see that depending upon the simulation, which is the route which is preferred by the controller, which are based on the different parameters associated with the path cost, amount of queuing, amount of network usage parameters like we have discussed previously. So we provide the script to find out about these elements, including path cost, best path, IDs associated with, and so on. Once we have done that, we show the results of the different paths. So you can see what is the result between H1 and H2, this between here and here, what is the result between H1 and H3, and so on, right? So those kind of things are shown over here, and then basically what are the data rates that you can get from there. Finally, we kind of try to, and this is using the RYU controller. Finally, we use the RL controller to supplement our work, and in this case, we have to, when we are going to RL, we have to kind of justify the use of RL. Our environment remains same as you see in figure 7, the network topology, that is our environment. But in our case, we have the RL agent. Now, in this case, we have used DQN as our RL agent, and then we have the rewards, which is basically the bit rates that you can get, and then states as which of the paths is it choosing and going between the two routers and the edge nodes, as well as the actions, which is basically choosing the right edge nodes. In this case, we see our simulation environment, which is GIM API, and it uses GIM middleware, which is primarily an environment in Python and supported by OpenAI GIM, which supports the proxy network environment through this network environment gateway, wherein our network model is situated. Once we have this network running, we see the results that we obtain through the RL environment, and you can see from the RL environment results comparison in the figure 13 that typically compared to load balancing shown in green, RL environment performs similar to some extent for lower number of calculations less than 150, but if you go beyond it, load balancing gives way to RL, and then the performance of RL kind of takes up, and which is expected because RL has the environment of learning. So when it learns more, it is able to perform better. So, and these are the list of references which comes with our paper. Thank you for your audience, and we sincerely appreciate you listening to us. You can always reach me, and you can reach me at my email ID, which is shown here, as well as the email ID of my colleague. Thank you again. Bye-bye.